Okay, Assalamualaikum and good morning. So today we'll continue with the lectures. But again, as I mentioned, I'm still typing up all the notes. So I will have to use the whiteboard again. So let me share my screen first. Okay, so let's go to the whiteboard. I hope you can see it. Are you seeing the whiteboard?
Yes, sir.
Okay, so what we have done so far is to just recall, we are looking at essentially systems that form canonical ensemble. And a few things we derive. So what is canonical ensemble? So systems are interacting with a heat bath, and essentially one of the things that one can do is to think of this heat bath as a replicas of the system itself, and then one calculates a few things that we have done in the past. Essentially, we look at the configurations. Okay, so we look at configurations W, and then we calculate your entropy, and finally some other thermodynamical variables. And of course, we need to use the idea of energy states with essentially eigenvalues epsilon I, and then for each of this state, one can associate probability through some statistical mean using this configuration, the different configurations. So I'm not going to repeat. So you just have a look at the previous notes or in the book. Okay, and we come to okay. The other thing that we have done is to, for the probabilities, you get the Boltzmann equation, the Boltzmann distribution. Sorry. Okay, so and what else? Just to recap, I think that's about it. Oh, and then of course the partition function. Okay, so you have this idea of partition function Z, which in the beginning we think of it as a normalization factor, so that your sum of your probabilities is equals to 1. But see that, okay, one can give some physical meaning to this partition function through the idea of free energy. Let me find out what's the formula for that. Yeah, F equals to minus kBT log Z. So recall that your Z connects the idea of this energy states, which comes from the microstate, Now it connects with thermodynamical variables through this free energy. So that has been done in the previous lecture. So today we're going to continue with this idea. My notes are pretty scattered here, so let me push this up. Okay. So given that you have done all this, and the next thing that we want to do is to consider changes. So here we are looking at other thermodynamical quantities. From log Z. Okay, so right. So what one can do is to consider small reversible changes in F such that the number of particles basically is kept constant there, and essentially if you do the differential, so you get df, this is from your previous thermodynamic section, df equals to minus p dv minus s dt, and from there essentially you can see that your p is given by minus df dv, okay, and this is coming from there, so you want to keep that t to be constant, so that's that. And then the other one would be your entropy minus df dt kept at constant v. Okay, so I need that. So now your f is now given in terms of a partition function. Okay, so in other words, if you simply substitute f as this function of this partition function into the expressions over here, then you'll be able to get, here now one gets these thermodynamical variables written in terms of your partition function. KB, so that is the f dv, so that means partial d log z partial v kept at constant t, and then your entropy is given by kb partial t log z partial t kept at constant v. So there you can see from here your Z contains your microstates, okay, connected to your thermodynamical variables or thermodynamical quantities. One could actually do further than that. It looks back into your thermodynamics sections or nodes. Okay, there are other quantities that one can actually define from your pressure and your entropy, so one can do that. Further further quantities that can be calculated. Oops, can't write too fast. So let me just, oops, I don't want that. Is an example is isothermal compressibility. So we can look it up. What's the formula for that? This is denoted by K, but the one that being used are usually given in terms of the inverse, where you do the differential or the derivative of your pressure with respect to the volume. Okay, so how the system responds to the changes in volume. Okay. And this, if we just simply use what we had above here, then this will give you something which is related to the second order derivative of your free energy. Okay. So the other one, with respect to entropy, one can now, this is probably more familiar to you, the heat capacity at constant volume. Put this up. Then again, you have heat capacity is given by notation CV equals to T ds dt. And this again will relate to your second order derivative of your free energy. And remember, your free energy is expressed in terms of your partition function. So more or less what happens over here, you can almost calculate all quantities. Quantities can be derived from free energy, and hence your partition function. Okay. The other thing over here one can observe, these are sort of derived quantities from a much basic quantity of the pressure and entropy. So these are sometimes called, since it's changes with respect to P or S, these are sometimes called the response functions. Response function. Okay. And this response function are usually written in terms of the second order derivative. Okay. Second order derivative of f. Okay. So what else do I need to show? Okay, one last thing is to just to recap the earlier thing that we had was actually the internal energy. That was related to your free energy in this way. Now, since S is now given in terms of your log Z, okay, and F is also log Z, so one can combine this. So T, KB, partial T log Z, T constant V plus your F is minus KBT log Z one could sort of do the derivative of this first. So you see some things get cancelled out. So derivative of the T log Z with respect to T, you can take the derivative of that T. So what you get is TKB log Z. And you can almost immediately see that this is going to be cancelled with that. I hope you can see my cursor. Can you see this?
Yes, Doctor. No. Yes, Doctor.
No or yes? I got two answers just now. Okay, okay, never mind. So I'm going to write everything down anyway. So plus T KBT, and then going to take the derivative of that. That T KBT is coming from that T, so I'm leaving out that T and take the derivative of log Z, and that is d log Z dt. This is just repeating then you can see that this cancels out. And what's left is that you are able to express the over here, remember we are in canonical ensemble where your energy is not fixed for the system. So what is considered fixed? No, it's not fixed. Your energy can change, but you can calculate your average energy. So this is average energy. So your average energy is now being written as kBt squared partial log Z partial t. Okay. So now we have all these quantities. So as I said, all quantities can be derived from the free energy here. And then also, in other words, you can, from the free energy, get the relationship with the log Z thing. So that means everything is coming from the partition function. So one should, so the thing that we want to do next is to test these formulas with some simple models. So that's the next section of that book. Give me a minute to sort out my notes so that I can retype this everything back. Okay. Right. So today we're going to look at these simple models and try to calculate some of the thermodynamical quantities using the partition function. Okay. let's do this. So the simplest model that we can think of is a two-level system. So your two-level system are usually things like your spin half particle on a lattice, and then to differentiate between the two spin half, remember the spin half, there's a spin up and spin down. Okay. And the spin up and spin down are essentially intrinsic angular momenta that they carry magnetic moments. So in order to see the differentiation between these two states, one places this in a magnetic field. Okay, and essentially then you get your spin up state and spin down states to be differentiated by interacting with this magnetic field, and they give energies plus or minus mu b. Okay, so but we don't want to go into the details of this. Rather, we want to say, okay, the generic idea here. There are two states. There are two energy states. With values, with eigenvalues plus or minus epsilon. Yeah. Okay. So if you want to be more particular into what system that you're looking at, then you can go through all the physical ideas of spin half in a magnetic field. But for us, enough for us to just say that, okay, there will be energy states that correspond to a plus epsilon, and there will be another energy state with correspond to a minus epsilon. Okay. So remember, in order to make the connection with this canonical ensemble, remember we are supposed to interact with a heat buff, but now the idea is you have this heat buff is given by replicas of those systems. So let me just write that thing down. So consider ensemble of M, and I should say distinguishable at the moment, M distinguishable two-level systems. Okay. So one of them would be probably of the system of interest, and then the rest sort of plays the role of the heat bar. Okay. So then you can start writing down your partition function. So what is the partition function is to recall, okay, what is Z? Is Z equals to sum I E, and let me just check, I think it's E epsilon KBT. So of all possible energies. Okay, so in this particular case, then there are only two energies, plus and minus epsilon. So your Z is reduced to E epsilon KBT plus E minus epsilon KBT. So that's the simplest that you can get from what I call from physics, and because there's nothing simpler than a two. Well, there is something simpler, but the one with at least you can differentiate between energy states at the spin half case, or the two-level system. Okay, so remember you have done your partition function, so the next thing is to calculate your free energy. Because from free energy, then you can derive most of the things that we are interested in. So free energy, what is it? So you remember F equals to minus kBT log Z and then, well, we can just simply substitute that Z into your log, but let's make this a bit more systematic, because you can sort of think of this as a common factor of the two terms. So I'm going to bring it out. So I will get log of E epsilon on kBT. So the first term will just multiply 1, and the second term, essentially to get that, you need a negative 2. Okay. So this this whole thing is under the log. Okay. So now your because there are two factors. Okay. Your log. Hello. Somebody want to say something? Okay, maybe it's just forgotten to turn off the mic. So so your log of A times B is just log A plus log B. So I would have log of that plus log of that. Okay, so the log of exponential is going to be just the factor there. Okay, so that will give me epsilon on kBT, and then the log of that. Okay, so that's log 1 plus E minus 2 epsilon. So you can simplify this further, and then this becomes minus epsilon minus kBT log 1 plus E minus 2 epsilon kBT. Okay, so you have done your free energy, so that means one can use that expression now, the last expression, to actually calculate other things. So let's do that. So let's calculate entropy. So entropy is given by minus partial F partial T at constant volume. Okay, so oops, what happens? Okay. Something is happening here. I'm not sure what it is. Okay, so now the only term that seems to depend on T is going to be only the second term. Yeah. So there are two T's involved here, one the factor in front and the other is in the exponential. So let's do this slowly so that you can see. So in other words, you have to do a lot of differentiation when it comes to calculations in statistical mechanics. KB, and then you differentiate this t, so that means I just will have kb log of 1 plus e minus 2 epsilon on kbt. So that factor is done. So now I need to differentiate that. So that's plus. So I'm going to leave your kbt here in front. And then differentiate the log. And differentiate the log essentially gives you 1 over that. Okay, so I'm going to write that here. And then it looks inside this log. What is the expression there? Where is the t? The t is appearing the exponential. So again, if you differentiate an exponential, you're supposed to get your exponential back. So I will have that exponential 2 epsilon on kbt. And then what's inside the epsilon, what's inside the exponential, then you can see that, okay, I need to differentiate the exponent here with respect to t, and that gives me, let me just copy this thing down. Okay. It will be given me, so I have this constant factor there, 2 epsilon on kb, and then differentiate minus 1 over t with respect to t will give you plus 1 over t squared. Okay, so let's just simplify that, because we're going to calculate other things from the entropy now. So can I do any simplification? Well, I can only simplify the second term. So kb log 1 plus exponential 2 epsilon on kbt, and then let me just write down the thing here, 2 epsilon over t divided by e. Okay, here I'm sort of bringing this thing down over here, so that becomes an exponential 2 epsilon kbt, and then this thing bring down over here will just simply cancel off that, and that gives you 1. Okay, so that gives you the entropy for the two-level system, okay, for single particle interacting with the systems in the ensemble. Okay, so let me push this thing up. If there are things that you question, please raise, because I cannot see you. Don't type in the chat because I cannot read it. So you just have to voice out if there's any question. Okay, so what can be calculated from entropy here is your heat capacity. So heat capacity is given by CV. Hello? Huh? Anything you want to ask? Okay. Right. So T partial S. Yeah, better push this thing up. It doesn't like me to write at the very end. Partial S partial T. Okay, now one has to look. Okay, this is going to be a bit elaborate. In fact, I did this calculation twice because I got the first time wrong. So let me just show you what I did. So over here, there are two terms, okay, in your entropy. So the first term, essentially, you're going to differentiate that log term. So, and also remember there's a t outside multiplying this derivative. Okay, so I will have kbt, and then your differentiation of the log, remember you get the reciprocal 1 plus e minus, is that right? Yeah, e minus 2 epsilon kbt. And then remember again, that is differentiating the log, and then you look at the expression inside the log. There's an exponential here, so you need to have that exponential back again. And then inside the exponential, where is the t? The t is on the denominator. So again, you have all the, I think we have done this for the case of the entropy before. So I'm just going to write it down. 2 epsilon on kb on 1t squared. Okay? So that is the first term. Second term, there are, no, again, is a fraction kind of thing. So you have to look at the numerator and the denominator. So let's do the numerator first. So then I would have, remember we still have that t in front, so I will put that t here, and then differentiating that. So that would actually give me minus minus 2 epsilon on t squared. And of course, you only differentiate this one on the numerator. So I need to have the denominator as well. And then differentiate the denominator next. Let me just write it down so that 2 epsilon on t. Yeah, I have to push this thing up. Right. So you cannot see the one before. Never mind. I just write it down. So this is e 2 epsilon and kbt plus 1 squared, and then I need to differentiate that exponential, and then the thing inside the exponential. So better warm up your calculus, okay, because you have all this kind of calculations. So if you look at this, this will cancel off with that, and then this will gives you the expression just like that. Okay, so this will cancel out with that, and you can see that, okay, I have my 2 epsilon here, I have my minus 2 epsilon over here. This thing divided by that will give you that. So in other words, this whole thing, maybe I should put in red color here, will cancel out with that. Okay, so that simplifies thing, because no, otherwise you have to go through all these 3 terms, but you only need to look at the last term. So the last term over here, again, is there's a long, well, it's not that long. Anything which can fit a particular page is not long. So it's only 3/4 of my page. Let me just write it down. So this is, I'm just going to write it down so you can figure out for yourself. 4 epsilon squared kBt squared, yeah, squared, then exponential 2 epsilon on kBt divided by that square thing. So, I mean, generally one could stop there if you want to, but no, if one can simplify it, you simplify it. Okay, so here we can try to expand this. It gives you a function that you know, 4 epsilon squared on kBt squared. So I'm just going to expand this square at the denominator. So here, again, better push this thing up. Here is exponential 4 epsilon on kBt plus 2 times exponential 2 epsilon on kBt, and then plus 1. That's simply just squaring the denominator. But now, okay, I have this on the numerator, so I can bring it down to become exponential minus 2 epsilon on kBt. So just do that. So in other words, I'm dividing all the terms downstairs by that term. Okay. So that gives me 1 on, so exponential 4 epsilon on kBt divided by that will give you exponential, exponential 2 epsilon on kBt. This term divided by that will just give me 2. This term divided by that will just give me exponential minus 2 epsilon on kBt. Okay. But if you look at this again, no, well, it comes from experience, I suppose, but you can see that this is essentially your exponential epsilon on kBt. kBt plus exponential minus epsilon on kBt, the whole thing square. And remember, call cos hyperbolic cos x is exponential x exponential minus x divided by 2. So I have that thing just like your exponential x and exponential minus x over here. So I have a square, so I need to square that, so I get a 4, and that 4 is already there. Okay, so that gives us, okay, now I can write everything down as follows. With this thing is just simply given by your hyperbolic cos. And of course, again, and of course, this is now much simpler from the one before, okay, because it just put everything in terms of this hyperbolic cosine function. So now this is heat capacity, okay, so remember this is heat capacity, and heat capacity you can actually measure in the lab, okay. So one can, and also here there are dependence on your temperature. So one can see some behavior here. Note, if you increase your temperature, then the term of this argument of this hyperbolic cosine, so let me just rewrite this as x epsilon on kbt will decrease, and essentially, well, actually it appears there as well. So, and also your cosh hyperbolic cosine x goes to 1, okay, because it's near 0 in some sense. Okay? So then this thing approaches x goes to 1. So in other words, the temperature dependence for high temperatures will only depend on this 1 over T squared. So in other words, one can say that heat capacity at high temperatures decreases as that factor 1 on T squared. So one can do the same for the low temperature. So heat capacity at low temperatures, what will happen? This will essentially, if you look at that, what's going to happen is when T is going to 0, for example, going very low, this thing blows up. But you also have that thing competing with this hyperbolic cosine, and that is going to sort of override this so-called increase, okay, because your hyperbolic cosine involves exponential. Okay, so in other words, the exponential will overpower that factor over here. So that will again decrease as exponential minus 2 epsilon on k. So in other words, high temperatures it decrease, low temperature it decrease, so there will be a maximum. Okay? There will be a maximum in between, and you can find the graph in the book. Okay? And this kind of behavior can be tested if you want. Okay, and such behavior is sometimes called Schottky heat capacity. Okay, before it's about, okay, let me just finish a few things before we take a break. So the other thing that one can actually try to calculate is your average internal energy, which is given by this as before. Okay, so you have calculated your free energy, you have calculated your entropy. So let me just write the answer down so you can work it out. Or maybe, okay, I mean, it is again involving all this hyperbolic thing. Okay, maybe I'll write it from here. 1 to exponential 2 epsilon kBt plus 1 minus 1. And I will leave this as an exercise. I did it. I will already check it. This can be simplified into minus epsilon hyperbolic tangent epsilon kBt. Okay, so this involves a little bit some manipulation there. Okay, so I'll let you do the exercise. It should be fun doing this kind of thing, because once you get the hang of it, you get satisfaction of being able to derive it. Okay. What do I want to say next? Okay, so in other words, this is essentially the case of a single spin half in an ensemble. Now one can generalize this to the case so I have to push this out, otherwise it will cause me problem. Can generalize to n two-level systems. Okay. Here I should say single two-level system. A single two-level system gives you that. For n two-level systems, then you have your average internal energy to be minus n epsilon. So you just simply add up. Careful not to write too fast. And you have seen this before. Okay, this is go back to I think the previous chapter where you talk the case of the microcanonical ensemble. So let me just put it in the microcanonical ensemble. You have this formula u on epsilon equals to n hyperbolic tangent epsilon on kBt. And of course, when you arrange, it becomes similar to that. Now, what's the difference between these two? This one comes from a canonical ensemble. Okay. And in canonical ensemble, your internal energy can change because it can interact with the other systems from the heat bar. Okay, so the only thing that you can actually do is to compare the average energy, whereas over here in the microcanonical ensemble, your energy is already fixed. Okay, and this is for the case of the n spinner n two-level system. Okay, inside your microcanonical ensemble. Okay, so I stop here at this stage to take a break, or do you prefer not to break? Why is it not appearing? maybe I'll just minimize that. Okay. So do you want a break or do you want to go on? I have another one more system to look at. And then break. Okay. So we have a 5 minutes break and we'll come back about 10:07. Okay.
Yes, sir.
Okay. At least that thing works. So I will end now. So probably we have to discuss when can we replace the lecture. Okay. So please discuss this among yourself. I better turn everything off. Right. So I think that's all for today at the moment. Okay. Thank you everyone.